Okay, so in this video we're going to talk about what acids and bases are. So if we're going to talk about acids and bases, we need to talk about pH. So pH is a measurement of hydronium. So essentially it means power of hydronium. So hydronium is H3O+, which is really just a water molecule bonded to an H+. So just so you know, if we talk about hydronium, if we talk about protons, if we say hydrogen ions, it really all talks about the same thing. So you might see it as H+, or you might see it as H3O+. A lot of people will use these terms and symbols interchangeably. Okay, so pH tells us how much hydronium you have in a solution or a substance. So pH will range from 0 to 14. So the closer you are to the pH of 0, the more concentrated the hydronium is. So you'll have more and more hydronium. As you go to 14, you get less and less hydronium. So if you have a pH that's below 7, your solution is considered to be acidic. If it's above 7 to 14, it's considered to be basic. So acids and bases are both electrolytes. So they both will conduct electricity. So if you have a solution that has an acid or base, it will conduct electricity. So acids will have a sour taste, while bases will have a bitter taste. Now, if we were going to test to see if it's an acid or base, we can use various indicators. We can also use a pH probe. We could also use litmus paper. So if I were to have an acid and put litmus paper into it, it turns it red. If it's a base, it'll turn it blue. Now, bases have a slippery feel to them. And a lot of them can be found in cleaning products. Now, antacids also contain bases, so they'll contain things like bicarbonate or carbonate or hydroxide. And an antacid will be used to neutralize stomach acid. So if you have acid reflux or if you have heartburn, it can help neutralize your stomach acid. Baking soda is also considered to be basic. So a lot of times when we bake, we'll have an acid component. So even in milk you have lactic acid, or you'll even maybe add a little bit of vinegar, and then baking soda. Well, when you put those two things together, it produces carbon dioxide, which makes the whatever it is rise. Now, acids will typically react with most metals to form hydrogen gas, especially more reactive metals. Now, acids are found in pretty much all of our food. So if you pick up something, you'll see that maybe it has citric acid or something along those lines. Now, when we talk about acids and bases, we actually have 3 different definitions that we use. We use the Arrhenius definition, we use Bronsted-Lowry, and then we also have something called a Lewis acid and Lewis base. We don't really talk about Lewis acids here because it's more important for organic chemistry. So Arrhenius acids form hydronium ions in a solution. So when you add it to water, you're going to make hydronium. Okay, so under the Arrhenius definition, if you have something and you put it into water and create hydronium, that would be considered an acid. An Arrhenius base is something that will form a hydroxide ion. So if I take ammonia and I put it into water, I'm going to create hydroxide. Okay, Bronsted-Lowry definitions, this is the one that we primarily use. Acids are going to be proton donors. Bases are going to be proton acceptors. So you cannot have an acid without a base here. So if I'm looking at this particular reaction, HCl with water, that hydrogen gets moved to the water to create hydronium. So this would be the acid. This would have to be the base because you have to move that proton and you move it over to the water. So the water accepts it, the acid donates it, and then with Bronsted-Lowry, we also have something called a conjugate acid and a base. So the acid donates the H+, and on the product side, it becomes the conjugate base. The base accepts the hydrogen and becomes the conjugate acid. So essentially, if you were to reverse this reaction, this would behave as the acid, this would behave as the base. So let's look at this one right here. We have water and we have HNO3, and I'm trying to figure out which one acts as the acid, which one acts as the base. So you have to pay attention to the hydrogen being moved. So HNO3 becomes NO3 minus. It has lost a hydrogen. H2O becomes H3O plus. So it has gained a hydrogen. So that makes water, in this case, the Bronsted-Lowry base. And then HNO3 is the acid. Well, the base becomes the conjugate acid, and then the acid becomes the conjugate base. So let's look at this one. We have NH3 and H2O, so pay attention to your hydrogen. So NH3 becomes NH4. So we have gained a hydrogen. H2O becomes OH, so we've lost a hydrogen. So acids will donate, bases will accept. So NH3 accepted an H3, or an H plus. So that makes that the base, and then the water will be the acid because it donates the H. So NH3 becomes NH4, so the base becomes the conjugate acid, and then the acid becomes the conjugate base. And if you notice, we use water in both of the reactions. Water is amphiprotic, which means it can be a Bronsted-Lowry acid or a base because it can donate an H. It can also accept an H. It just depends on what it's interacting with. All right, so let's give the conjugate base for each of the following. So if we're going to give the conjugate base for these, we're going to take off an H plus. So you're going to take off an H, but don't forget you're taking off an H plus, so the charge will be different. So HF becomes F minus. So you're taking off the H, and then you have a charge of 0. Okay, so right here you have a neutral charge. Okay, you're taking away a positive 1. So that becomes negative 1. All right, so now let's look at H3O plus, H3PO4. So you're going to take off just one hydrogen, and don't forget the charge is now going to change. So we have a 0 charge here. We're taking off 1 proton, so we're taking away one positive 1. That gives me a negative 1. So it should be H2PO4 minus. All right, so H3O plus, take away just one hydrogen, okay? So we're gonna have H2O, and then now you've got a positive 1. You subtract 1, you're gonna have a charge of 0. It becomes water. Okay, so just a note here, if you have these acid-base pairs, they can only be different by one H plus. So if I had H3PO4, okay, H3PO4 and then PO4 with a -3 charge, these are not conjugate acid-base pairs because they are different by more than one H plus. So it can only be a difference of one H plus here. Okay, so polyprotic is also a special term. It's an acid that has more than one H plus. So H3PO4 is polyprotic because I can take off more than one hydrogen. It's just you can only take off one at a time. All right, so give the conjugate acid. So in this case, okay, this is a base. Bases accept, we're gonna add an H plus. So if we're gonna do that, it's going to become HBr, charge will change, so now you're adding an H plus, so it's -1 plus 1, which would be 0. So HSO4, this is the base, bases accept, so add an H plus, so it's now going to be H2SO4, and then the charge will change as well, so -1 plus a positive 1 will give me 0. All right, so now let's do this one. Add an H, just one H, and then we have a -2 charge plus a positive 1, which will give us a -1. So this will be -1. All right, right, so let's look at acid strength. Okay, a lot of times people will confuse acid strength with not only how corrosive or dangerous an acid is, or also the pH. Okay, so pH refers to how concentrated it is with hydronium. Acid strength actually depends on something else. So acid strength refers to how much the acid ionizes in water. pH talks about how much hydronium you have in the solution. Okay, so a strong acid is not necessarily a corrosive acid. So if you watch Breaking Bad, hydrofluoric acid was mentioned in one of the episodes, and it is a dangerous acid. It's very corrosive. However, it is not a strong acid. It is a very weak acid, because strength refers to how much it ionizes in water. So when we talk about something that ionizes, okay, that means that I put it into a solution and I create ions. In the case of an acid, we're talking about hydronium. How much hydronium will you make if you put it into a solution? Okay, so our strong acids, we have 7 of them. Memorize them. Okay, so we have hydrochloric acid, hydrobromic acid, hydroiodic acid, perchloric acid, sulfuric acid, nitric acid, and chloric. You need to know those. The good news is once you know those 7, everything else that's an acid is considered weak. Organic acids are going to be weak acids. So anything that's oic acid, like propanoic, ethanoic. Ethanoic acid is also acetic acid. Any acid that's not on this list is a weak acid. Okay, strong bases are going to be the group 1 and the group 2 hydroxides. Weak bases, so once you know strong bases contain hydroxide, like the group 1 and group 2, everything else is weak. So ammonia, anything with the word amine in it, those are going to be basic, but they're weak. Okay, so a strong acid and a base will ionize pretty much 100% water. So whatever you have in there, it's going to ionize completely. It's going to break apart and make lots and lots of ions. It's a very strong electrolyte. So anything that's on that list, those 7 acids or bases that contain hydroxide, those are strong electrolytes. Weak acids and bases will be weak electrolytes. So what does it mean to be a strong acid? Okay, let's say that I have this. This is an acid. It's got hydrogen on it. So if it's a strong acid, let's say that I have 5 of these. I have 5 moles of this, and I put this into a solution. So once I put it into my solution, what'll end up happening is that everything will break apart into ions. So I'll have H+, that's the first one. The second one will do the same. The third one will do the same. Fourth one will do the same. And then the fifth one will do the same. So it ionizes completely when you put it into a solution. So how much ever acid you put into the water, that's how many ions you create. That's how many hydronium ions you create. Or hydroxides, if we're talking about a base. Okay, so weak acids and weak bases do not ionize completely, and they are weak electrolytes. So if you were to have a weak acid or a weak base, okay, let's say that I have the same situation. I have 5 moles. And then I dump it into a solution. Okay, well, maybe one of them will ionize, but most of them are going to stick together. They're just going to be water molecules. So you do create some ions in this solution, but not a lot. So weak acids do not ionize completely. They ionize to a very, very small extent. So when we put them into water, we're not going to make that much hydronium. So weak acids and weak bases, if we were to put the same amount of a strong acid as a weak acid, so let's say that I have 1 mole per liter of a weak acid and 1 mole per liter of a strong acid. Well, pH is the measurement of hydronium, which is this, okay? If I have a weak acid, I don't have as much hydronium in there. My pH is going to be higher. If I were to have a strong acid, everything will ionize completely and I will make more of this, and my pH will be lower. Okay, so acid strength refers to how much it ionizes or breaks apart when you put it into water.